Measurement systems are indispensable for the modern production industry, and for a resource and cost-efficient production, measuring directly in the production line is clearly preferred to classic laboratory measurements. However, process and vibration-induced motion blur has so far limited the achievable measurement precision. A new generation of measurement systems is required to deal with relative sample motion and offer a performance comparable to laboratory-based measurements. Imagine you're sitting in a moving train, and the landscape outside is rushing past your field of view. If you focus on a fixed point on the window, the scenery appears blurred. But your eyes naturally respond. They quickly compensate for the relative motion of the passing landscape to stabilize the image and generate a sharp perception in your brain. This same concept can be used to precisely position the measurement system relative to the moving sample to generate local laboratory-like conditions. This is a 3D CAD model of the designed 3-degree of freedom positioning system. Core part of the system is the metrology platform incorporating the optical measurement system, which is moved along the production line. A standard spindle drive with a stepper motor is used for the coarse positioning, reducing system complexity and costs, and providing extendable travel ranges. To overcome the low positioning precision of spindle drives, a dual-stage approach is applied. Therefore, the coils of 3 cylindrical Lorentz actuators are mounted on the pusher, which is connected to the spindle drive. The magnet parts of the actuators are fixed at the metrology platform, allowing the positioning of the platform in 3 degrees of freedom by applying forces from the back. It is suspended on the machine frame by linear roller guides on either side of the frame. To counteract manufacturing and mounting tolerances of the linear guides, mechanical flexure mounts are designed to enable sufficient motion freedom, which allows the Lorentz actuators to precisely position the metrology platform over the entire motion range. This animation illustrates how the system tracks the motion of the measurement samples along the production line. By doing so, it enables highly precise 3D measurements, similar to those achievable in a static laboratory environment. Simultaneously, disturbing vibrations originating from the spindle drive or surrounding machinery are actively suppressed by the advanced control of the Lorentz actuators. Let's look at the control system. We start with a physics-based model of the metrology platform and its flexure mounts. It describes the motion in 3 generalized coordinates. From the actuator geometry, a mapping matrix W is built that converts voice coil forces into the generalized forces of the model on the platform. To enable the use of 3 simple individual Tissot controllers, a modal decoupling approach is used. A transformation matrix U transforms the system equations into modal coordinates. In the ideal case, the modes are independent, so each controller can focus on one mode. But there's a catch. The linear guides can be either stuck due to stiction or moving, which changes the system dynamics. Therefore, 2 separate models and the respective decoupling matrix for each case are derived. A smooth transition function lambda is used to blend between those 2 models during operation. When the platform moves along the production line, the coarse spindle drive keeps the relative distance to the pusher constant. This is accomplished by a second control loop tracking the relative distance between pusher and platform, measured by optical proximity sensors. This keeps the voice coil actuators within their allowed actuation range. For the positioning experiments in the paper, a trajectory generator generates smooth reference position trajectories for the controllers. The experimental setup is shown next. The metrology platform performs a constant velocity scan at 10 millimeters per second. Performance is evaluated by the worst-case lateral measurement error epsilon. Defined as the maximum lateral measurement error an optical measurement system mounted on the platform would make due to motion errors. This plot shows the evaluation of this error over time. The baseline case in blue, with the spindle drive alone, reaches errors up to 0.7 millimeter. With dual-stage actuation, the error can be vastly reduced to 7.5 micrometer over the entire range. The lower subplot shows the voice coil actuator forces, correcting the spindle imperfections and external disturbances. The second run shows a scan speed of 100 mm per second, illustrating the dynamic capability of the system. Currently, the limit is set by the coarse positioning unit and could be further increased by different actuation principles depending on the specific application. The designed 3-degree of freedom dual-stage actuated positioning system is a first step into next-level inline metrology systems, which offer lab-like measurement precision directly on the moving samples in the production line. A decentralized control approach based on modal decoupling is presented, and a resulting measurement error of 7.5 micrometer is achieved, which is a vast improvement compared to the coarse positioning system alone. Enjoyed the video? Subscribe to the channel so you don't miss out on upcoming research. For papers and project pages, visit our institute homepage. Thanks for watching.